Good morning, Mr. Marvin. Since it's morning right now, that's why I'm saying good morning. So this is Okello Andrew Peters, and I'm going to be presenting a paper. Let me straight away first share the screen. Yeah, so this is our presentation. I'm going to be presenting a paper titled Computationally Efficient Breast Cancer Classification Using Vision Transformers and Efficient Net, a hybrid approach with quantum genetic algorithm for regions of interest selection and hyperparameter optimization. The group members are Hadija Athman and then Okello and Repeaters. Those are our details. So, introduction. Breast cancer is one of the most common cancers in women, with approximately 2.3 million women globally diagnosed annually, according to the World Health Organization report. Early detection is important for improving survival rates, with mammography still as the gold standard for screening. However, traditional diagnostic methods tend to be slow and are often prone to human error, which can lead to false positives and false negatives. So, to overcome these challenges, deep learning has turned out to be a transformative method in the classification of breast cancer, providing greater accuracy and efficiency. Convolutional neural networks such as ResNet, DenseNet, and MobileNet, as applied in studies, have shown excellent effectiveness in feature extraction and classification. However, these models have some challenges which I'm pointing out now. The first challenge is optimization techniques. So the optimization techniques for feature selection and model training, despite advancements in deep learning models, optimizing feature selection and training remains a significant challenge. Meta-heuristic algorithms such as particle swarm optimization, PSO, genetic algorithm, GA, have been used for hyperparameter tuning and feature selection, thus improving efficiency. Some recent studies we looked at used the PSO for hyperparameter optimization along with CNN in breast cancer classification, achieving accuracies exceeding 90%. And another challenge is the region of interest in mammograms. Like, that is also important. So, what is our problem statement? So, while CNN architectures have achieved high accuracy in breast cancer, in breast cancer classification, they present major computational challenges that hinder real-time clinical deployment. Mammograms contain high-dimensional information, making deep feature extraction computationally expensive. Existing regions of interest selection techniques such as OTUSU, the paper I read was used OTUSU for extracting local features. So OTUSU thresholding and UNet introduce false positives and increase processing time. Furthermore, hyperparameter tuning methods, including greedy search and genetic algorithms, suffer from long convergency times and suboptimal solutions. So addressing these challenges requires an approach that enhances feature extraction efficiency, improves regions of interest segmentation, ROI segmentation, and optimizes model hyperparameters in a computationally effective manner. So what is our proposed solution? So this study proposes a hybrid approach that combines efficient net. So efficient net extracts local features using depth-wise convolutions and compound scaling, reducing spatial redundancy before passing before passing information to the vision transformer. So up here you can see a structure of an efficient net. We got it from Google Images. You can see that it has conv 3x3 filters. Efficient net starts with this regular 3x3 convolutional layer to capture low level features like edges and textures. in that image, it's capturing edges like textures. Then the next layer here we see is an MB convolution 1 3 by 3. MB stands MB's MBs are called depthwise separable convolutions. Instead of standard convolution, EfficientNet uses the MB convolution blocks, which includes the depthwise convolution. Each input channel is convolved separately, reducing computation. It also includes pointwise convolution, which merges information across channels. It also includes the sequence and excitation SE block, which improves feature representation by reweighting channels. So this first MB convolution, this first MB convolution has an expansion ratio of 1, meaning it doesn't expand channels but deeper, MB convolution 6 use expansion factors like 6. So efficient scaling strategy. EfficientNet applies compound scaling, depth scaling, which increases the number of layers, width scaling, which expands the number of channels per layer, resolution scaling, which increases input image size for better classification. So why did we use EfficientNet for local feature extraction? These MB convolution blocks allow efficient extraction of spatial hierarchies. The SE blocks, which I mentioned earlier, enhance important local features. Then the lightweight design makes it more computationally efficient than traditional CNNs like ResNet. So the other thing we are using are vision transformers. So these vision transformers capture global dependencies using self-attention mechanisms, enhancing feature representation for accurate classification. We may use Swin Tiny due to limited computational resources, since we are going to use Colab for implementing this architecture. What you can see here at the right, this is the structure of how a vision transformer operates. It starts with patched images. So the initial step of the VIT model, the input image is reshaped into a sequence of 2D patches with dimensions P by P expressed. So the P is the dimension of the patch which to the different sequence of patches you want to create. So this reshaping step allows the VAT model to treat an image as a sequence input and then leverage the self-attention mechanism to extract relationship between patches. So there is also, the moment these patches are then flattened, so that into a format that the vision and transformer can understand. Then this diagram here, this transformer encoder, is what we pulled out here and tried to show that it has the normalization, multi-head attention, normalization, MLP, which is multi-layer perceptron. Yeah, so that is, we shall go deeper as we are explaining. So this study proposes a hybrid approach, which also combines you've seen the first two now. The other thing is the quantum genetic algorithm, which optimizes hyperparameters, EG learning rate, dropout rate, the vision transformer, patch size, and refines the region of interest selection to focus on the most relevant mammographic features. So let me first explain the methodology, then I'll go to the what? I'll go to the computational challenges. So what is our methodology? Remember, we are doing a binary classification with the vision transformer, and we are going to be using a multi-layer perceptron. A multi-layer perceptron is just a network of dense layers to output a binary output. So the classification task is formulated as a binary classification problems where mammograms are categorized into benign and malignant classes. Our dataset is in-breast dataset, which has those different images in separate folders. So the approach consists of the following. So we are going to start with mammogram images, which are going to go through a meticulous, vigorous EDA, so that we can have pre-processed mammogram images, so that we can have clear and nice predictions. So EDA, my friend is going to do the EDA video where we are showing you what we did. We had to check for class imbalance, then we do some data augmentation to oversample the minority class to be equal to the majority class. We had to do some denoising, we had to do some cropping to remove artifacts, we had to do some increase brightness, contrast, and all that in the EDA. So after the EDA here, we output pre-processed mammogram images which enter efficient net. So efficient net is for extracting local features, reducing spatial redundancy, and it outputs feature maps. These feature maps are flattened. Remember, the vision transformer expects an input, a sequence input. So that is why we have to flatten and reshape these feature maps so that they are in that format. So the output out from here is the patched image or sequence of patches which enter the vision transformer. The vision transformer processes all this and it produces processed feature embeddings which go through quantum genetic algorithms so that they are further optimized. The quantum genetic algorithm randomly generates initial hyperparameters and regions of interest sections. It then evaluates fitness. It uses classification using classification performance as the fitness score. Then it updates parameters by applying quantum-inspired mutations and crossover. Then we choose the best candidates for hyperparameter tuning and regions of interest refinement. Then we output optimized hyperparameters and refined regions of interest, which then go into these refined VIT features through the quantum genetic algorithm. They now go into the fully connected layers, which is the multi-layer perceptron. We apply nonlinear transformation through activation functions, which is ReLU in this case. Then in our output, the last layer in the densely connected layer will use the activation function called sigmoid to do binary, to output a binary output. And yeah, so basically that is how are we addressing computational challenges? I'm rushing because I'm running out of time. The first one is vanishing gradient mitigation. We are using ReLU because ReLU is used in we are going to use ReLU in hidden layers to ensure effective back propagation. Vanishing gradient is where the gradient of the earlier layers vanishes, where it makes back propagation kind of impossible. So another challenge is computational efficiency. So we are using efficient net, like explained, for feature extraction, reducing the dimensionality before VIT processing, reducing computational overhead. Another thing, the optimization strategy, the quantum genetic algorithm will be leveraged for hyperparameter selection and regions of interest segmentation, improving convergence speed and classification accuracy. The rest of the details are in the concept note. That is what we had. Thank you very much.